Welcome to Astronomy 1301. This is Dr. Miles Blanton. The ancient astronomers observed that objects in the sky moved, and so that's precisely what we're going to do today, is to talk about the motion of the objects through the heavens. And we're going to see what we can learn about the nature of the universe just by observing these motions. Much of this lecture, Motions in the Heavens, is covered in Units 5.3, 6.1, 8.1, and Unit 11 from your textbook. Observing the motions of the heavens involves using one of the simplest scientific models that we develop in astronomy. A scientific model is a simplification or a picture version of some form of reality. The celestial sphere is one of the simplest scientific models. We can imagine the celestial sphere is an enormous sphere surrounding the Earth with all of the objects of the heavens painted on this sphere. Now, we know this is not an accurate reflection of reality. We know that the stars are very far away, but not an infinite distance away. We know that stars have different distances. Some are nearby, some are farther away. But it's useful to think of all of the objects in the sky sort of painted on this imaginary celestial sphere. It's useful, although it's not a perfect, accurate reflection of reality. Now, one thing we can see from this is to talk about the daily motion of everything in the sky. We can consider that the celestial sphere revolves once per day, and all of the objects attached to the celestial sphere therefore move through the sky once per day. In particular, we can talk about how fast the stars, for instance, move throughout the night. If all of the stars go through the entire celestial sphere once per day, that means that one revolution occurs per day, 360 degrees in a day, 24 hours. 360 degrees in 24 hours is 15 degrees per hour. And so when we talk of how fast the stars move, that's what we mean. The stars move at 15 degrees per hour, regardless of where they are in the sky, unless they're exactly at the north celestial pole, which is very near where the North Star is. All of the other objects in the sky are subject to this diurnal motion. And again, this is we can consider this to be the celestial sphere rotating once per day. Now, of course, we know as 21st century individuals that what's really happening is that the Earth itself, as a solid object, is spinning, and so it gives the appearance of all of the things moving through the sky, even though it's the Earth itself that moves. Apart from the daily motion of the sun rises in the east and sets in the west. This is the diurnal or daily motion of the sun. The sun also moves against the celestial sphere apart from this daily motion. As the Earth orbits or revolves around the sun appears to move through 13 constellations on a belt around the celestial sphere that we call the ecliptic. So as the Earth moves around the sun, the sun appears to pass in front of, and therefore blocking, due to its glare, these 13 different constellations. Now, a quick note, you may be familiar with the 12 zodiac constellations. There is another constellation, less popular, in between Scorpius and Sagittarius, called Ophiuchus. So when the sun blocks one of these 13 constellations, we say that the sun is in this constellation. As the sun moves around the ecliptic throughout the year, it passes in front of all of these 13 constellations. Now, the direction is very important. Relative to the background stars, so relative to the entire field of the celestial sphere, the sun travels west to east throughout the year. So remember, this is contrary to the diurnal motion. So once a day, the sun rises in the east and sets in the west. So throughout a single day, the motion of the sun due to diurnal motion is east to west. But very, very slowly, relative to that motion, west to east, across the ecliptic, the sun travels through the entire celestial sphere relative to the background stars once in a year. This is the annual motion of the sun. So, for instance, we can consider the motion of the sun throughout the year. And so in leaps and bounds, very, very slowly, the sun travels west to east throughout the year. So for instance, in June, the sun is in Taurus, contrary to the actual zodiac sign. In June, Gemini is mostly what June is. But in June, the sun is actually in the constellation of Taurus. Traveling along the path of the ecliptic, about a month later, the sun will be in Gemini. So west to east, Taurus to Gemini is west to east. Gemini is further east than the sun, or than Taurus. A further month after that, the sun will be in Cancer, traveling from Gemini to Cancer, and in the course of about a month. So June is in Taurus, more or less July is in Gemini, August is in Cancer. Another month goes by, and the sun is now in Leo. So in the month of late August, early September, the sun is in Leo. So we'll do this throughout the entire zodiac and through the entire ecliptic. And so it takes a full year, all the way around back to June, before it is once again in Taurus. So the sun and the moon travel along the path of the ecliptic, more or less the same plane in the sky, and they travel very constantly. The sun and the moon are very constant. The sun takes about a year to go all the way through the celestial sphere along the path of the ecliptic, and the moon takes about a month to go all the way through the celestial sphere. But they do so constantly. They don't slow down, they don't change direction. The sun and the moon travel constantly and directly. And this motion is west to east. So this is in the opposite direction than diurnal motion, but on a much smaller, or a much slower time scale. Now the planets, the other planets that we consider, most of the time they also do the same thing. Most of the time the planets travel west to east from night to night, and they travel at different rates. So the Mars and Venus and the other planets take different amounts of time to travel through the entire celestial sphere. But those planets do something else that's a little bit weird. From time to time, they will slow down and they will travel backwards relative to their normal path for a little while, and then they will resume their direct motion. So most of the time, they follow the same direction of motion as the sun and the moon. From night to night, west to east. From time to time, they will slow down and change direction over the course of typically many months, or many weeks, or many months, and travel east to west. This is referred to as retrograde motion. So here we have an image of the retrograde motion of Mars, taken over the course of several months, from not necessarily night to night. This image was taken probably one image a week, and we see in the beginning on the right hand of the image, that's the west side of the image, the first loop is from west to east, and then it slows down, changes direction, and moves backwards for about 2 months, and then resumes its path once again. So in the period that it's going east to west from night to night, this is referred to as retrograde motion. Early models of the solar system attempted to explain the motion of all of the things in the heavens, all of the things that we're seeing, and to sort of put them all together into a single model of the universe. Most early models of the solar system, which we would consider a model of the universe, all of the things in the universe being taken into account, early models of the universe place the Earth at the center of all of the motion of everything in the sky. All of the things in the sky moved in circles around the Earth. Now this is fine for things like the moon and for the sun and even the stars that move constantly, that don't have any changes to their motion. The motion of the planets, in particular retrograde motion, however, was a problem for these earliest models. Circles do not get along with retrograde motion. In particular, they did not do a good job of predicting future positions of the planets. Indeed, that is what makes a good scientific model, is whether or not good predictions could be made. Now, for the moon and for the sun, good, accurate predictions could be made using this model. Indeed, we can see that the importance placed on planets, and for a moment we need to step back and say that for the earliest models, the sun and the moon were also considered planets. Literally planet. Planetus means wandering star. And so those 7 objects, the sun and the moon, but also Mercury, Venus, Mars, Jupiter, and Saturn, these 7 wandering planets, actually kind of formed a very powerful distinction from the stars. The stars were very constant. These 7 wandering planets were not. And we can see this, how it's sort of filtered down through the years by the astronomical association we have with the 7 days of the week. Indeed, some of them are fairly obvious. Monday, Moon Day, but even in Spanish, which is the only language I can probably speak without completely butchering the pronunciation. Lunes in Spanish, we can see that's related to the moon. Tuesday, Martes in Spanish, so that's definitely Mars related. That's Tuesday, Thursday in Norse, Tyr from Norse. Wednesday, Miércoles, Mercury's day. It's also Woden's day, is where we get the English word for Odin in Norse mythology. Thursday, Jueves in Spanish, Jove's day, the Roman Zeus, the Jupiter, the largest or most important god in Roman mythology. Of course, the English word Thursday, Thor's day. Thor, of course, being from Marvel Comics, or the Norse god of thunder. Friday, Viernes, Venus's day in Spanish. Fria's day from Norse again. Our English word comes from Norse. Saturday, Saturn's day. Fairly straightforward. Of course, Sunday. No modification needs to be made to get Sunday out of that. So these 7 objects were very important to ancient cultures, and we see that as those names have filtered down into our present day language as well. And so these 7 objects the motion of these 7 objects need to be taken into account in forming any model that understands their motion and explains and makes predictions about their motion. Welcome to Astronomy 1301. This is Dr. Miles Blanton. So recall from our last lecture, we have a unified set of observations for the behavior of the sun, the moon, and a general description of the retrograde motion of planets. So we have this starting point with all of the observations of the actual reality of the night sky, and our task now is to figure out how to put those observations together to figure out what is actually going on to give us these observations. The retrograde motion of the planets in particular serves as this sort of pivot point for understanding the complex nature of our universe. This historical presentation of solar system models and the arguments between them figures into Unit 11 from the textbook. Early models of the solar system attempted to explain the motion of all of the things in the heavens, all of the things that we're seeing, and to sort of put them all together into a single model of the universe. Most early models of the solar system, which we would consider a model of the universe, all of the things in the universe being taken into account, early models of the universe place the Earth at the center of all of the motion of everything in the sky. All of the things in the sky moved in circles around the Earth. Now this is fine for things like the moon and for the sun and even the stars that move constantly, that don't have any changes to their motion. The motion of the planets, in particular retrograde motion, however, was a problem for these earliest models. Circles do not get along with retrograde motion. In particular, they did not do a good job of predicting future positions of the planets. Indeed, that is what makes a good scientific model, is whether or not good predictions could be made. Now, for the moon and for the sun, good, accurate predictions could be made using this model. One of the first very successful models to actually explain the motion and make good predictions was by Ptolemy in the 1st and 2nd century CE, after the Common Era. And he improved on these earliest geocentric models. So this Ptolemy's models still place the Earth at the center of all motion, but each planet that displayed some kind of retrograde motion, in addition to moving in a circle around the Earth, also moved on a circle on top of that circle called an epicycle. So this circle upon circles made sort of a spirograph pattern. This somewhat artificial seeming, certainly to modern humans, modern cultures, this very artificial epicycle did actually a really good job of predicting the future position of planets. And that really is the hallmark of a good scientific model, is whether or not it makes good predictions of future observations. Any scientific model that's worth its salt has to be consistent with observations that have already been made, but a good scientific model also needs to be consistent with future observations as well. And this epicycle model did exactly that. Though it seems very artificial to us, it is actually a good scientific model because it made good predictions to the best observations of the day. Here we have an animation showing you that sense as well. Prograde, retrograde, and then prograde once again, or direct. Prograde and direct are the same. As you have no doubt guessed, the Ptolemaic version of the universe, the Ptolemaic model for the solar system, is not the model that we use today. We today, ask anyone on the street, the Earth goes around the sun. Now, Copernicus is most famous for bringing this idea that the Earth actually goes around the sun to our modern consciousness. Now, he is certainly not the first scientist to suggest that the Earth revolves around the sun. It's probably better to say that he was the last. After Copernicus, there was not much contention about the question of whether the Earth revolved around the sun or the other way around. Now, one of the linchpins of the Copernican idea that the Earth should revolve around the sun is that this makes retrograde motion very easy to explain. Like your first instinct, I'm sure, when you heard of the epicycle model of Ptolemy, Copernicus did not like the excessively complex and artificial nature of the epicycles to explain retrograde motion. In Copernicus's model, all of the planets revolve around the sun, and they do so on perfect circles, with one exception, and that is the moon. The moon, exactly like in Ptolemy's model, the moon revolves around the Earth. So all of the planets, including the Earth, move around the sun on perfect circles. And this does a very good job of explaining retrograde motion as well. In the Copernican model, retrograde motion is well explained by the relative motion of the planets as they revolve, all of them, around the sun. So, for instance, we have here the Earth and we have Mars. The planets closer to the sun move faster on their orbits. This is also another part of Copernicus's idea. The Earth is closer to the sun than Mars, and so the Earth is revolving around the sun faster. As it does so, occasionally the Earth will pass Mars in its orbit, essentially lap it in its orbit. When Earth is close to Mars, it does this when it's close to Mars, for a little while Mars appears to move backwards. So as the Earth passes Mars, as it sort of catches up and passes Mars, Mars for a little while appears to move backwards. And so it's only because of this faster and slower motion, the inner and outer motion, that we have this apparent motion of retrograde motion. And so this is just an apparent phenomenon. This is not an actual phenomenon. In Ptolemy's universe, the planets actually move backwards because of this epicycle behavior. In Copernicus's universe, this is just an apparent effect. This is not due to actual motion in the backwards direction. So Copernicus's model is very consistent with our previous observations of, say, the sun. The sun rises in the east and sets in the west. According to Copernicus, This is due to the rotation of the Earth on its axis, this is our modern conception. The sun appears to move through the celestial sphere once per year, the annual motion of the sun through the ecliptic, through the zodiac constellations along the ecliptic. This is due to the Earth revolving around the sun. Ptolemy's model suggests the exact opposite, that the sun goes around the Earth, and that's why it appears to move through the constellations. Copernicus's model also does a good job of explaining a peculiar behavior of Mercury and Venus. Mercury and Venus are always bounded by some angle to the east or to the west of the sun. Now, Ptolemy was able to explain this by specifically tweaking the size and speed of his epicycles. But in Copernicus's model, the bounded nature of Venus and Mercury's position in the sky relative to the sun, Mercury always less than 28 degrees from the sun, east or west, and anywhere in between. Same thing with Venus, except for 47 degrees to the east or west of the sun, and anywhere in between. This is due to the fact that Mercury and Venus are inner planets, or inferior planets to the Earth. And all the other planets can be anywhere in the sky relative to the sun because they are superior planets, planets that are farther from the sun than the Earth is. This is very well explained by Copernicus's model. So we have a set of observations. We have the daily motion that all things are subject to. All things rise in the east and set in the west. This daily motion from moment to moment is east to west. We have the yearly motion of the sun. So throughout the course of a year, the sun travels west to east along the ecliptic through the entire celestial sphere. We have the monthly motion of the moon as it also passes through its phases, also west to east, taking about a month to progress more or less along the ecliptic. And then we have the peculiar motion of the planets. So from night to night, most of the time traveling also west to east, more or less along the ecliptic, but occasionally traveling in retrograde motion, east to west, for several weeks or even several months. We also have the fact that Venus and Mercury behave differently than Mars, Jupiter, and Saturn. Venus and Mercury are bound on either side, east and west of the sun, whereas Mars, Jupiter, and Saturn are unbound and can be anywhere in the sky relative to the sun. Now, before we move on to understand how we place these separate observations in the context of models of the solar system, let us consider a quote by 20th century philosopher Ludwig Wittgenstein. He says, "Tell me, why do people always say it was natural for man to assume that the sun went round the earth rather than the earth went round the sun?" He told this to a friend. His friend replied, "Well, obviously, because it just looks as though the sun is going round the earth." Wittgenstein replies, "Well, what would it have looked like if it had looked as though the earth was going round the sun?" So, of course, the underlying paradox here is we have an observation. And let's just take the sun, and the observation is the sun, in a given day, rises in the east, passes high in the sky, and sets in the west. Throughout the year, relative to the background stars, the sun travels west to east through the entire ecliptic. That's what the sun does. Our interpretation of that is subject to our model. And this is precisely where Copernicus and Ptolemy both enter into the equation. So we have separate observations. We have an observation that the stars exhibit, and everything in the sky exhibits, diurnal motion, rising in the east and setting in the west. Ptolemy's explanation for this observation is that the entire celestial sphere and everything in it rotates around the Earth once per day. Copernicus's explanation for this observation is a little bit different. Copernicus's explanation is that the Earth itself is what rotates once per day. We have the observation, the sun exhibits its annual motion, west to east along the ecliptic throughout the celestial sphere. Ptolemy's explanation for this annual motion of the sun is that the sun revolves around the Earth. The Earth is stationary and the sun moves around it once per year. Copernicus flips this around. The Earth itself revolves around the sun. That's his explanation for this observation. The moon exhibits its monthly motion of motion through the celestial sphere and its monthly cycle of phases. Ptolemy's explanation, the moon revolves around the Earth, and fortunately Copernicus's explanation is exactly that as well. The moon revolves around the Earth. The changing position of the relative location in space between the sun and the moon and the Earth gives us the differing phases, but whether the sun revolves around the Earth or the other way around has no effect on the motion of the moon or the phases of the moon. Finally, we have the observation of the planets. The planets exhibit retrograde motion. That's the troubling and special observation. Ptolemy's explanation for retrograde motion is that each planet moves on its own epicycle, in addition to its orbit as it orbits around the Earth. Whereas Copernicus says, no, all planets move on circular orbits around the Sun, including the Earth, and it is the relative motion and the fast, slow, different in speeds of the planets. Close planets move fast, far planets move slowly. It is this relative motion that gives us retrograde motion. So we have these two competing models to explain essentially the universe. In particular, we have the comparison of their different explanations of retrograde motion. So Ptolemy's model of the universe places the Earth at the center. All the planets move on circular orbits about the Earth. And all of the planets that exhibit retrograde motion have their epicycles to explain retrograde motion. Copernicus's model places the sun at the center of the universe. All of the planets move in circular orbits about the sun, the moon moving in a circular orbit about the Earth. This gives us an easy retrograde motion, since Mercury, Venus, Earth, Mars, Jupiter, Saturn is the order of the planets. The inner planets move faster than the outer planets. The relative motion of the fast planets to the slow planets gives us retrograde motion. So the question is, now what? We have two competing models of the universe. If we find ourselves in Renaissance Europe, where Copernicus's model is in competition with Ptolemy's model, it's very important to keep in mind that in Copernicus's day, both of these models did a good job of predicting the future position of the planets. And that is the hallmark of a good scientific theory. A good scientific model makes good scientific predictions. At this point in history, in the day of Copernicus, both models give us the same precision of predictive value. And so it is our question now, what do we do with this information? What do we do next? How do we distinguish between these two models? So it's at this point that I want you to ask yourself and sort of examine within yourself what you already bring to the table as a 21st century individual. What do we know, but more importantly, how do we know it? Some questions to consider. So as a 21st century individual, what is the organization of the solar system as you know it? I will offer my own example of an answer to this. What is the organization of the solar system? It's the sun. The sun is at the center, and the planets orbit around the sun. The planets are in the order Mercury, Venus, Earth, Mars, Jupiter, Saturn, and then, of course, we're also aware of Neptune, or Uranus and Neptune as well. But we can ask, what does Copernicus's model of the universe prove? What does Copernicus's model of the universe even demonstrate? Copernicus's model suggests that all of the planets move in circles around the sun, and that the Earth is a planet. But what does it actually prove? We need to wonder, how do we even start to distinguish Copernicus's model from Ptolemy's model? They're both very different from one another. They are different examples or representations of reality. Copernicus's model suggests that the sun is the prime mover of all things. Ptolemy's model suggests that the Earth is the prime mover of all things. How do we distinguish between these two? How do we answer the question, does the Earth revolve around the sun? How do we know that that's the actual accurate representation of reality. We certainly know that's true. And we were 21st century individuals, so we asked the question, does the Earth revolve around the sun? Does the Earth orbit the sun? Absolutely. Yes, we know, absolutely. The question facing us in the next few lectures is, how do we know that that is true? So, as I end today's lecture, I want you to ask yourself, how do you know? What is the process that you have gone through in your life that leads you to here today, knowing already the answer to the question, does the Earth revolve around the sun? Welcome to Astronomy 1301. This is Dr. Miles Blanton. So today we pick up with our mystery that we're trying to unravel about what is the nature of the universe. No small task. The key at this point to further our distinction between a heliocentric or a geocentric and to expand on Kepler's laws really requires observation. We have two physical models of the universe, and both models adequately explain the observations. Both models adequately explain the motions of the stars, the sun and the moon, and the planets with their retrograde motion. Ptolemy's model places the Earth at the center. All of the planets move in circles around the Earth, and all of the objects in the sky are planets that move. And in addition to these circles, the retrograde planets all have epicycles to explain their retrograde motion, so circles within circles. Copernicus's model, more than 1,000 years after Ptolemy, places the sun at the center, all of the planets moving in circles about the sun, and the Earth is a planet. The one exception, of course, is the moon. The moon moves in a circle around the Earth. Copernicus's model gives us this, what I'm calling easy retrograde. The relative motion of the planets, inner and outer, give us retrograde motion. So, how do we distinguish these two models? Before we dive into a discussion to further divide these models, I want you to consider orbital motion and consider various shapes in which orbits could move. Both Ptolemy's model and Copernicus's model hinge upon circles. So let's consider some other shapes that we might consider for orbits. Certainly we could think of a square orbit. It certainly sounds preposterous, but that's as valid a shape as any. Other shapes to consider beyond circles, ovals or even open shapes that don't close back on themselves, tracing various patterns. So you can just consider different shapes. With various shapes in mind, let us consider actually observing the trace of an orbit and figuring out exactly what the size and shape of that observation is. So for instance, let's take this object here, this trace, and consider the size and shape of this figure. You might take a moment and find a ruler and actually measure and try to figure out exactly what this shape is and also the size of this figure. Having considered the size and shape of the previous figure, well, how about this picture? What is the size and shape of this figure? You might be able to see a little more clearly that it's not quite so symmetric. It's a little bit oblong. So what's the difference between the previous shape and this shape? Certainly the narrowness of the line greatly affects how you can measure the size and shape of either figure. On my computer screen, this figure is about 19.5 centimeters in one axis and about 18.5 centimeters on the other axis. So it's very clear that this is not a circle. This is not perfectly symmetrical. This is, in fact, an ellipse. So the precision and the clarity of the image is extremely important in determining the true shape. And really this idea, this underlying idea of the precision of your data, brings us to our next topic of today's lecture, which is
In the textbook, Kepler's laws are covered in Unit 12, although we'll be using this and other parts of Unit 12 for a good chunk of the remainder of the course.
So one way we can distinguish between competing scientific models is just to take new data, to take new and better data. And at the forefront of the crusade for better data was an astronomer named Tycho Brahe. As you can see from the dates, he's born around the time of the death of Copernicus, so he's a full generation or so after Copernicus. Tycho Brahe was obsessed with making precision measurements, and so he built new instruments that were state-of-the-art with a precision of, the best precision of about 1 arcminute. So this is about a 60th of a degree. So you take the entire sky is 180 degrees. Every degree can be further subdivided into 60 arcminutes. Tycho Brahe was able to measure the position of objects in the sky to a precision of about a 60th of a degree, 1 arcminute. Prior to Tycho Brahe's measurements, the precision of astronomical measurements was to about a half a degree, or about the same size as the full moon. A star or a planet could be anywhere within an area about the size of the full moon. So comparing that to Brahe's measurements, those are very imprecise. So in addition to making precision instruments, Tycho Brahe was an astronomer and observer in his own right. And he was one of the first people to demonstrate that comets were outside of the Earth's atmosphere and not nearby phenomenon. He also was lucky enough to see a supernova. More on that in about 15 lectures. But this was a new star, a very bright new star that brightened and then went away. So he saw that some phenomenon were outside of the Earth's atmosphere, that the heavens were changing, but he could not detect the parallax of stars, and so he didn't believe that the Earth revolves around the sun. He thought the sun revolved around the Earth. But he did agree halfway with Copernicus. He said all the other planets, or he believed all the other planets revolved around the sun, but then the sun and all those other planets revolved around the Earth. In astronomy, we always introduce Tycho Brahe because his protege, Johannes Kepler, is who's remembered for making great advances in astronomy. But it is Tycho Brahe's data that Johannes Kepler used to advance our understanding of the motion of the planets. And using Tycho Brahe's superior data, this very high precision data, Kepler discovered that the planets did not move in circles around the sun, as Copernicus said, but they followed ellipses, where the sun was located at one of 2 foci of the ellipse. Now you can make an ellipse by taking 2 thumbtacks and a loop of string and using a pencil, pulling the string taut and pulling it around in a arc, keeping the loop around the 2 thumbtacks. And this is a shape similar to an oval, similar to a circle, certainly, but distinctly different overall in character. So using Tycho Brahe's high precision data, Kepler found that the planets move in elliptical orbits. Do you remember the ellipse has 2 foci, 2 focuses? The sun is located at one of the 2 foci. There's nothing special about the other focus of the ellipse. This is just where the sun is located at one of the foci. And note that this did not agree with the ancients. This did not agree with Brahe. This didn't even agree with Copernicus, not in the fine detail that Copernicus had. Copernicus demanded a circle of the motion. Kepler's first law of planetary motion modifies Copernicus's model. Now, within the orbit of an elliptical orbit, we focus on 2 additional points called the aphelion and the perihelion. And this is specific to orbits of objects around the sun. Note, helion means sun. So aphelion is the farthest point from the sun. We can always think of away. Aphelion is away. And perihelion is the nearest point to the sun. Think proximate. So perihelion is proximate. And we often will use aphelion and perihelion to talk about the orbit of planets. Kepler also discovered that the velocity of a planet changes throughout its orbit about the Sun. And he developed a very geometric and sort of artificial sounding relationship that has to do with the velocity of a planet. So his artificial geometric description, this is Kepler's second law, is that if we take a line that connects the planet to the Sun, and we imagine that line as the planet sweeps around in its orbit, marks out an area. So that line sweeps out a wedge of the orbit. If we take some time interval, so 2 months is the example given here in the image, and we look at a 2-month interval of any part of the orbit, that line that sweeps out an area, that area will be the same for any 2-month interval. So any amount of time interval on the orbit will sweep out the same area as any other part of the orbit. Now what this amounts to physically is that when planets are close to the Sun, near perihelion, they move faster than when that same planet is far from the Sun, near aphelion. So faster sweeps out a wider wedge, but more squat, being closer to the Sun, and a slower, farther wedge is swept out that's more narrow. This also explains the non-circular behavior of planets. So since this is a somewhat artificial geometric description, so a line joining the planet and the Sun sweeps out equal amounts of area in equal intervals of time, we can sort of do an example here. So for instance, if we sweep from B to C, and where each of these steps is, say, a month interval, the area swept out from B to C is this white wedge as given. And if we compare this to some other 1-month interval, F to G for instance, the area swept out by that line is the same. Now, for circular orbit, which is just fine, there's nothing violating of any of Kepler's laws to have a circular orbit. A circle is just an ellipse with the 2 foci at the center. In a circular orbit, since the areas are identical and the distances traveled in each of these 1-month intervals is also the same, this means that the planet is moving at a constant speed throughout a circular orbit. This is not the case for a eccentric orbit. So both a circle and an ellipse are ellipses, but an eccentric orbit is not a circular orbit. In an eccentric orbit, as displayed here, the distance between each of these equal interval steps is different. So if we have an interval, again, say a month, far from the Sun, A to B, this sweeps out a very narrow but very long wedge. Closer to the Sun, say F to G, it's a much wider wedge, but a little more squat, being closer to the Sun. And then say I to J, again a month, the area of this wedge remains the same, indicating that the planet is speeding up and slowing down. So in this case, A to B, the planet is moving fairly slowly. F to G, the planet is moving near its fastest. Kepler's first 2 laws of planetary motion are somewhat geometrical in nature. Kepler's third law, the other relationship that he found using Tycho Brahe's very detailed, very precise data, was a mathematical relationship between how long a planet takes to orbit the Sun, its period, and the size of its orbit. And we characterize the size of a planet's orbit by its semi-major axis. So Kepler found that the relationship between the period and the semi-major axis obeyed this equation, p squared equals a cubed, where p is the period and a is the semi-major axis. Now it's important to note that these 3 laws of planetary motion are empirical in nature. What this means is Kepler made observations, or rather Tycho Brahe made observations, but Kepler, using observations, found that these relationships and these laws worked. There is no underlying logic, or there is no underlying physical principles at work. This is just essentially pattern solving. So Kepler was able to identify very simple, straightforward patterns in the data. There's no underlying physical law that that decrees that these laws of planetary motion must be true. At this point, we're going to get to physical laws that describe this. So Kepler's third law is a mathematical relationship between the semi-major axis and the period of the orbit of a planet about the Sun. So there are a few important reminders for that we have to keep in mind to make sure that we can use this equation correctly. One is that this is the law for a planet in our solar system orbiting the Sun. So this will not work, for instance, for the Moon orbiting the Earth, or say a moon of Jupiter orbiting Jupiter, or any other object other than a planet in our solar system orbiting the Sun. This also will not work directly for some other planet orbiting some other sun. The relationship is going to be a little bit different. This is also important to keep in mind that we use the appropriate units when using this equation. So for the semi-major axis, we're going to be using units of AU, and for the period, we're going to be using units of years. As we see, this is very appropriate for the Earth. So for instance, the semi-major axis of the Earth's orbit, by definition, is 1 AU. That's how we define the astronomical unit. For the period of Earth's orbit is 1 year. So just a very simple example of the Earth, 1 year squared is equal to 1 AU cubed. And so this is unitized to the properties of the Earth's orbit. All right, so let's look at a quick couple of examples of actually calculating something from Kepler's third law. So for instance, suppose we know that the distance that Mars is from the Sun is 1.5 AU. Let's find the period of Mars's orbit. So p squared equals a cubed, so that means that p is equal to the square root of a cubed. A is 1.5 AU, so we plug a into this equation. And our next step is the square root of 1.5 to the third power. 1.5 to the third power is 3.375. We take the square root of that, and we get 1.8. So that means that the period for Mars's orbit is 1.8 years. So it's very important to keep in mind that it's very tempting to say, oh, well, Mars is 0.5 AU farther away from the Sun than the Earth is, so perhaps it's 0.5 years longer in its period. But as we see here, that is not the case. The period of Mars's orbit is 1.8 years. Not obviously connected to how much bigger its orbit is, which is why we use the equation in the first place. This relationship, p squared equals a cubed, is so not intuitive that it's also not surprising that it took until the late early 1600s before anyone discovered this relationship between the size of an orbit and the period of the orbit. So for instance, if we have Jupiter and we measure how long it takes Jupiter to go all the way around the Sun, and that takes 11.9 years, how far is Jupiter from the Sun? P squared equals a cubed. We want to find a. So we take the cube root of both sides. So a is the cube root of p squared, p being the period of Jupiter. So remember, we can rewrite this as p squared, all of that taken to the 1/3 power, or just period to the 2/3 power. Then we can just plug and chug. Period is 11.9 years. 11.9 taken to the 2/3 power is 5.2. 5.21. So that means that the average distance that Jupiter is from the Sun is 5.21 AU. Again, this is not an intuitive relationship, so it's fortunate that Kepler was able to discover this mathematical relationship so we could make these calculations. To remind you of the nature of orbits, let's consider a couple of right and or wrong pictures. So here we have this red orbit. What is right and what is wrong with this picture as it relates to actual orbits of actual planets? Well, we note that the Sun is not at the center of an ellipse. An elliptical orbit, the Sun is not at the center of the ellipse. The Sun is at a focus. Which focus doesn't matter. It's a symmetrical along the line of the focus. So it doesn't matter which focus the sun is at, but the sun has to be at a focus. Here we have the yellow orbit with the sun off-center. The yellow orbit seems to be mostly circular, and so given a mostly circular orbit, the foci, the two focuses, are both located at the center of the circle, and so for an ellipse of eccentricity equal to 0, a circle, the special case of an ellipse, the sun will be located right at the center of the circle. So what have we learned today? So very simply, we have Kepler's 3 laws of planetary motion. Kepler's first law is that all the planets move in ellipses with the sun at one focus. Kepler's second law says that a line connecting the planet and the sun will sweep out equal areas in equal amounts of time. The physical understanding of this, of course, is that planets move faster close to the sun and slower farther from the sun. We have Kepler's third law, which is a mathematical relationship between the period of the orbit and the semi-major axis of the orbit, p squared equals a cubed. Once again, we're still dealing and wrangling with this question, does the Earth revolve around the sun? And we're not yet to a complete answer for how we know the 21st century response, which is, of course, yes.
Welcome to Astronomy 1301. This is Dr. Miles Blanton.
So today we pick up with our mystery that we're trying to unravel about what is the nature of the universe. No small task. And so today we're going to pick up the pieces with starting with Ptolemy and Copernicus. Who is right about the universe? Is the sun the center of the universe, or is the Earth the center of the universe, or some other model? So how do we begin to distinguish these two models? Speaking of observations, we still don't yet have definitive evidence that Copernicus is right or that Kepler is right. Kepler's model is a description of reality that works. There's still no compelling evidence that he's absolutely correct, other than to come up with 3 simple rules to explain the universe is fairly remarkable. To further refine our ability to distinguish one reality from another, we introduce the observations of Galileo.
The content of this lecture is reviewed in Unit 12 of the textbook.
Galileo is famously the inventor of the telescope, although he didn't actually invent it. He, using a Dutch-designed telescope that he built himself, he saw a spyglass and he essentially built one for himself, and he improved the invention. But he is likely the first, at least in recorded history, to point his telescope at the sky and actually make observations. And he did a number of remarkable observations guided with his telescope. Keep in mind, Tycho Brahe's instrument, though remarkable in precision, was still naked eye. It was not enhanced using optics. So a summation quickly of Galileo's observations, and we'll devote an individual slide for each of these. He observed sunspots. Not a good idea to do, by the way, to point your telescope at the sun, but he observed craters and mountains on the moon. He observed the 4 moons of Jupiter. Jupiter has a whole lot more moons that we're aware of now, but these are the 4 biggest. He observed the rings of Saturn, although he didn't quite know what they were, but he recognized that Saturn had something peculiar going on with it. And most important to our discussion today, he observed that Venus passed through phases, just like the moon does, although the order and nature of the phases of Venus is somewhat different than the order and nature of the phases of the moon. So even apart from all of these wonderful observations that he did, Galileo is also considered sort of the grandfather of modern mechanics. So his advances to our understanding of the principles of motion are very, very important, but that is for another discussion. So before we get to a discussion of Galileo's observations of the phases of Venus, which are the most important of all of these observations, I'll introduce some of the earlier observations, or less pertinent to our discussion. So Galileo observed that the sun had imperfections upon its surface. This was also one way to demonstrate, since these imperfections moved, one way to demonstrate that the sun itself rotated. So the sun was thought previously to be a perfect sort of Platonic ideal object, but showing that it had a changeable surface. These sunspots came and went and moved across the face of the sun, showed that the sun was not a perfect Platonic object, that it was a real object like anything else. This is essentially the same sort of significance to the features of the moon that Galileo observed. He observed shadows and distinct contours on the moon that we know now as craters and mountains, but he demonstrated, and these are sketches shown here, that the moon is also not a perfect, smooth sphere. Galileo was the first to observe the moons of Jupiter. The 4 large moons of Jupiter, now called the Galilean moons after Galileo, Io, Europa, Ganymede, and Callisto, orbit Jupiter on timescales of many hours to a few days, depending on how close or far they are from Jupiter. So this was the first evidence that something orbited something else, and that sounds silly to state it in words, but it's actually quite profound. This whole argument of whether the Earth revolves around the Sun or the Sun revolves around the Earth essentially was just a tug of war between which was more important, the Earth or the Sun. Well, here was Jupiter, just a wandering star, who itself seemed to have a system of satellites that didn't care whether the Earth or the Sun were supreme, but cared only about moving in relation to Jupiter. So this is just evidence that not everything has to orbit either the Sun or the Earth, that some other object could be the prime focus of some object's motion. Here we also have Galileo's observations of the rings of Saturn. Now, again, he didn't know exactly what they were. His telescope was not quite high enough of quality or precision to see what we see today as the rings of Saturn. He kind of thought of them as ears, but they were changeable. So as Saturn orbits the Sun, it's the angle with which we see Saturn changes. So sometimes we see the rings more face on, sometimes we see them more edge on, and so these things, whatever they were, came and went over the course of many years. Before we dive into what is arguably Galileo's most important observation, I wanted to take a step back and go over something that you might have thought I skipped over the first time, and that is the phases of the moon. Not only does the moon move, certainly through diurnal motion. Remember, everything in the sky rises in the east, sets in the west. This is diurnal motion. The moon also moves more or less along the ecliptic, relative to the background stars. And in the process, it also goes through, we're very familiar with, the phases of the moon. So what is responsible for the phases of the moon? It's actually the motion of the moon, and the phases of the moon are connected. So as the moon moves through its more or less monthly cycle, about 29.5 day cycle, one half of its surface is always being lit by the sun. So the sun shines and lights up the part of the moon that is facing the sun. However, the part of the moon that's facing the sun is not always the part of the moon that's facing the Earth. So for instance, when the moon is on the far side of the sun from the Earth, so when the sun, the Earth, and the moon more or less make a straight line, only then is the part of the moon that faces the sun also the part of the moon that faces the Earth. So we see a fully illuminated surface. As the moon moves in its orbit around the Earth, less and less of the moon, from the full moon onward, less and less of the moon is lit up from our perspective. So in this diagram here, as we move from 5, fully lit, to 7, half of the moon is still lit up, but we don't see all of that half that is lit up. We only see a part of the moon that's lit up. So we would refer to this as third quarter. and then as the moon continues on in its orbit, and the sun, moon, earth more or less make a straight line. Not a perfect straight line. We always get a solar eclipse. More or less straight line. We see very, very little of the illuminated surface of the moon. Almost all of that illuminated half is facing away from the earth. We refer to this as new moon. Then as the moon continues on, down from 1 to 3, we would refer to that as first quarter. So the full moon, 5, would really be second quarter, but we refer to that as full. Now, from our perspective here on Earth, this motion of the moon is the moon traveling relative to the stars of the celestial sphere. And because the plane of the orbit of the moon and the plane of the orbit of the Earth are more or less the same, the moon appears to travel along the ecliptic, a little bit off the ecliptic from time to time, and it also travels in the same direction as the sun. So this is also west to east, but this is a much longer time period. So everything subject to diurnal motion, rising in the east, setting in the west. Apart from that, in the course of about a month, the moon travels west to east through the entire celestial sphere. So it travels approximately a 12th of that every day. Or sorry, a 24th of that every day. We come now to probably Galileo's most important telescope observation, and that is of the phases of Venus. Recall that the moon goes through phases, and this is due to its relative position in space between the sun and the earth and the moon. And so while half of the moon is always illuminated, it's only the half facing the sun, and we don't always see that same half. We see from our perspective as the moon revolves around the earth, we see this changing perspective of the illumination of the moon. Well, the same thing can be true of Venus. Indeed, Galileo observed that Venus went through a series of phases. But he also saw that it changed size, and the relationship between in what range did it change size, and how did it change phases with its changing size. This helped us to illuminate the motion of Venus. Now let's take a step back for a moment and imagine that Ptolemy is right. If Ptolemy is right, then all of the planets and everything in the universe orbits the Earth. If that's the case, then Venus is always in between the Sun and the Earth. Venus is on its orbit around the Earth, so the Sun is on its orbit around the Earth, and even despite its epicycle motion, Venus is always in between the Sun and the Earth. Well, if Venus is always in between the Sun and the Earth, sometimes it's near the Earth, so it appears bigger, and sometimes it's farther away and appears smaller. If Venus is always in between the Sun and the Earth, then the light from the Sun, as it reflects off of the surface of Venus, would only be a glancing blow. The light from the Sun would always be illuminating the sunward side of Venus, and we would only catch glimpses of that sunward side as Venus was far off to the east or to the west relative to the Sun. And so what this means is if Ptolemy is right and all the planets orbit the Earth, then Venus would always exhibit a crescent phase. We would always only see a sliver of the light reflected off of Venus from the Sun. However, what Galileo saw was dramatically different. Galileo saw that Venus went through all of the phases, just as the moon does. So from full to crescent and gibbous and half and nearly new. So what this means is, at some point, Venus must be on the far side of the Sun from the Earth, so that when Venus is nearly fully illuminated, that light reflects off nearly the full surface of Venus, and so it must be on the far side of the Sun from Earth's perspective. This is also consistent with the fact that when Galileo observed Venus near full phase, so gibbous, Venus was also small. So that would mean it's on the other side of the solar system from the Earth. As Venus moves around in its orbit around the Sun and becomes on the near side of the Sun from the Earth, the light just glances off of one limb of Venus, and so we see it as a crescent phase, however, much larger. So this progression from a large crescent to getting smaller but more full, and then back again, demonstrates that Venus must orbit the Sun, that Venus cannot orbit just the Earth. Venus must orbit the Sun. Now, this seems like then the perfect evidence for all of our argument. However, we have to be very careful. This is only evidence of what it's evidence for, and this is only evidence for Venus orbiting the Sun. Now, it is very straightforward to make the leap that if Venus orbits the Sun and Earth is somewhat like Venus in its size and its shape, then perhaps Earth orbits the Sun, and that's a good argument, but it's not itself evidence. The phases of Venus are evidence only for the fact that Venus orbits the Sun. However, that does give us supporting argument for that the Earth should then also orbit the Sun. But it's very important to make that logical distinction. So where do we stand now after having considered both Kepler and Galileo? We want to ask what our current understanding of the way the solar system is, sort of from this historical journey. So we have Kepler's laws. These are empirical laws of his observations of the position of the planets, and this supports a heliocentric universe. Kepler's laws only work if the Sun is this central focus. Now, it is a modification of Copernicus's model in that the planets do not move in perfect circles at constant speed. They move in ellipses with changing speed, and we have the details of how the relationship between the period and the semi-major axis of each of these planets. So we have this new ability to calculate things from orbital parameters. But it's in support of this heliocentric universe, although it is not itself evidence, because these are empirical laws. These are just rules that work with the data. Galileo's observations certainly supports a heliocentric universe, but only conclusively for the case of Venus. There's no other way that we can conceive of configuring the universe such that the observed phases of Venus match anything other than Venus orbiting the Sun. And so that's not direct evidence that the Earth orbits the Sun, but it is a good argument. Even still, though, we only have a set of hows. We only have a set of descriptions of the way that the universe seems to be. We don't yet have an understanding or an answer for the question of why is this the way it is. And so that's where our next lecture and our leap to Newtonian gravity will bring us.